So let's move on from our Lewis structures and formal charge ideas and look at the molecular shape of molecules. Shape which can be predicted because of the electron pairs in the valence shell of an atom. So it's a little bit like looking at satellites around the Earth up in the atmosphere. If it's a prime objective of each satellite to avoid the other satellites, then you would expect them to space themselves out as far as possible and move as far away from each other as possible. And that's kind of like the electrons in the outer shell of a central atom in a molecule. Because the atoms are connected to each other in the molecule through covalent bonds. Those covalent bonds are made up of pairs of electrons. Electron pairs are electrons which are negatively charged, and negatively charged particles always repel each other. So while the electrons have got to stay in orbit in the valence outer shell of the central atom, they've also got to stay clear of each other, because if they get too close, they would be repelled by the other negatively charged electrons. So this is what we call VSEPR theory. We're talking about the electrons in the valence shell, that's the outer shell of the atom, and looking at these electron pairs, whether it's lone pairs, which are not involved in chemical bonds, or bonding pairs, which attach atoms together, and the repulsion between these electron pairs allows us to powerfully predict the shape of molecules. If we minimize the repulsion, we maximize the stability of the molecule. So let's look at the three basic shapes that we can get. When there are two chemical bonds around a central point, those chemical bonds, while staying in the valence shell, the electrons get as far away from each other as possible, so they stretch out to opposite sides of the molecule, stretching out and giving a bond angle of 180 degrees. If we add another bonding pair of electrons, so three chemical bonds around a central point, again the bonds, to minimize repulsion between each other, they stretch out as far away from each other as possible, and our bond angle is now reduced to 120 degrees. Now, our first two examples are molecules which are flat. But if we add a fourth chemical bond, the bonds now have to stretch into the third dimension, stretching out to look like a tripod stand, with a chemical bond coming straight out of the top of the tripod stand. It's keeping the electrons pairs as far away from each other as possible and creates a bond angle each time of 109.4 degrees, maximizing the bond angle to minimize repulsion and maximizing the stability. Now, when we get chemical bonds in these three contortions, with the two chemical bonds at 180 degrees, we've already seen molecules like this in the chapter notes. Molecules like carbon dioxide and hydrogen cyanide. Double bonds and triple bonds are treated like one entity. So one bond getting as far away from our second bond to create that 180 degrees angle, and we say the molecule is linear. Or a triple bond getting as far away from the single bond as possible while still in orbit in the valence shell of the carbon. They stretch out to opposite sides, creating that 180 degrees angle, and again this linear shape. With the three chemical bonds around the central point, again we've seen this in the notes, molecules like carbonate, the polyatomic ion, 1, 2, 3 chemical bonds, creating a bond angle of 120 degrees, and it's making up the points of a triangle flat with a table. So we call it trigonoplanar. Last one, with our 1, 2, 3, 4 chemical bonds getting as far away from each other as possible. Again, we've seen molecules like this, CH4 methane, and that shape is known as tetrahedral. If you've got the same number of chemical bonds, you'll get the same shape every time, because the electron pairs are repelling each other in the exact same way. There is a little bit of a twist to our story, however, because it's not always just bonding pairs of electrons in the valence shell of the atom. Sometimes we switch out bonding pairs for lone pairs. So let's take a look and see what this does to the shape and bond angles. So a trigonal planar molecule with 1, 2, 3 chemical bonds, if one of the bonding pairs becomes a lone pair, the electrons are still taking their position in the same basic stance, but now there isn't anything physically up at the top of the molecule. So all we see is just 1, 2, 3 atoms at this bond angle still of 120 degrees, but the shape of the molecule without an atom at the top is just non-linear. And again, through the chapter we've seen lots of examples like this. Examples where there's one lone pair and 2 chemical bonds. We've seen nitrite, NO2, 1-, the polyatomic ion, ozone, O3, it's a different form of oxygen gas, and then sulfur dioxide, SO2, all examples which are non-linear with a bond angle of 120 degrees because there's 2 bonds and a lone pair each time. Let's take a look at some of the variations on the tetrahedral molecule by starting to switch out bonding pairs for lone pairs. So we get rid of the bonding pair here and switch it for a lone pair. The relative positioning of the electron pairs is still the same, but because a lone pair is more repulsive than a bonding pair, the bond angle between the remaining bonding pairs has gone down to 107 degrees. And the shape of the molecule without the atom at the top is now known as trigonal pyramidal, which we sometimes in Great Britain call truncated tetrahedral. I'm fine with either name, just be aware if you talk about truncated tetrahedral, because the tetrahedron has had the top sawn off, that's not something most Americans will understand. They're all looking for trigonal pyramidal. And if you have the same combination of bonding pairs and lone pairs, 3 bonds and a lone pair, we get the same shape and bond angle each time. And we've seen this already with ammonia, a lone pair and 3 chemical bonds, and phosphorus trifluoride, a lone pair and 3 chemical bonds. The bond angle shrinks to 107 degrees, and we now call it trigonal pyramidal or truncated tetrahedral. Let's do that again and take another bonding pair and turn it into a lone pair. So now 2 lone pairs and 2 bonding pairs, and those lone pairs again create stronger forces of repulsion because the electrons are not being shared with another atom. Now the bonding pairs push slightly closer together to alleviate the stronger repulsion from the lone pairs, and the bond angle goes down to about 104 degrees. It's non-linear, as we've seen before, but it's because of a different number of lone pairs. Now 2 lone pairs creating this non-linear shape instead of the 1 lone pair that we had before. So with 1 lone pair, it's 120 degrees for the non-linear shape. With 2 lone pairs, it's 104 degrees for the non-linear shape. And again, we've looked at molecules with this design. Dihydrogen sulfide, 2 bonds and 2 lone pairs to give us non-linear, and the chloride ion, ClO2, 1-, 2 lone pairs and 2 bonds, creating that non-linear shape with an angle of 104 degrees between the remaining bonds. Okay, let's stop there and take a break, but we're going to come back and look at some example molecules next and build them up from scratch and work out the shapes and the bond angles for the molecule.